Assalamu alaikum everyone. I hope you're all safe and sound. Welcome to the fifth lecture on analog and digital electronic circuits, in which we will study small signal models for the bipolar junction transistor. As we all know by now, the emitter-based junction of the transistor in the forward active mode is modeled through a forward bias diode. So small signal modeling of the BJT requires us to carry out small signal analysis for the diode first. And then these results are used to construct two small signal models for the BJT, namely the hybrid pi model and the T model. Then we will study the early effect, which is a phenomena that makes the collector current dependent on the collector emitter voltage. And we will properly augment these two models, the hybrid pi and T model, to reflect this dependence. So I begin by showing these large-scale models for the BJT, which we have already seen in lecture 3. These are called large signal models because there is no constraint on the base emitter voltage. There is no limit on the base emitter voltage. And as can be seen, the forward biased emitter-based junction in these two models. So this is the T model, this is the pi model. So in both of these models, the forward biased emitter-based junction is represented by a diode, which is a highly nonlinear device. So the purpose of small signal analysis is to construct linear models out of these large signal models for the BJT in the active mode. So in order to construct linear models from these two models, we must first of all construct a linear model for the diode itself. So here I show a diode which is excited with the sinusoidal. So we assume that this small Vd is a sinusoidal source. So the diode is excited with a sinusoidal source and a constant DC voltage source, Vd. So this Vd, the purpose of this constant DC voltage source is to bias the diode in the forward mode. Because if you take this Vd out, then assuming that this small Vd is sinusoidal in nature, for the negative half cycle of this small Vd, the diode will enter the reverse mode. The diode will be reverse biased. So in order to avoid that, we must lift this small Vd, or in other words, we must add DC offset to this small Vd so that the overall voltage denoted by small v subscript capital D, this overall voltage is always greater than or equal to about 0.4 volts or so, because we know that that diode requires about silicon-based diodes, they require about 0.4 volts or so to fully start functioning in the forward mode. So the purpose of this DC source is to ensure that the diode keeps on conducting in the forward mode for the entire cycle of this sinusoidal source signal. So as mentioned, the total voltage across the diode is given by small v subscript capital D, and it is the sum of the DC voltage and the small AC voltage. So this is an AC voltage. Yes, I've mentioned that this small Vd has been assumed to be sinusoidal in nature. The corresponding current flowing through the diode in response to this voltage Vd is given by this expression. So it can be seen that the diode current has an exponential dependence on the diode voltage. So Vt is the thermal voltage, Is is the scale current. Or in the context of diodes, Is is also called reverse saturation current. So we can, as can already be seen from this relation, Id has an exponential dependence on Vd, and we can actually mathematically see the nonlinearity of this relation by first of all dividing this Vd into DC and AC source, denoting this DC term as Id, and then expanding this exponential function to Taylor series around 0. So this is the Taylor series expansion of this exponential function around 0, in which you can see that in addition to these linear terms, we have non-linear terms as well, and there are actually infinitely many non-linear terms. So this factorial, exclamation mark here represents factorial. So this is 2 factorial, 3 factorial. We'll have a term with 4 factorial in the denominator to the power 4. Then we'll have a term to the power 5 and so on. So there are infinitely many nonlinear terms in this expression, which makes this expression highly nonlinear. However, if we assume that this ratio of the AC voltage to Vt is very small, much smaller than 1, then its higher powers will be even smaller and hence can be neglected. So if this ratio is sufficiently small, so that its higher powers can be easily neglected, safely neglected, then we get an approximate linear relation out of this nonlinear relation, in which we have ignored all the higher order nonlinear terms. So now the diode current is given by the sum of the DC current and a term which depends on the signal alone, only signal itself. So I represent this term through small subscripts, small I subscript small d, like this. So the total diode current is now given by the current due to the DC bias, capital VD, and the small signal component due to VD, small VD. Small VD is now called the small signal because it satisfies this what is called as the small signal approximation. So this small signal approximation enables us to derive a linear relation, which is actually approximation, from this highly nonlinear representation. So VD will be called a small signal, small voltage signal, and ID is the corresponding small diode current. So ID is the response of the diode to the small signal VD. So like I said, ID is the small signal current flowing through the diode in response to the small signal VD. Now, from this relation between ID and VD, we can find the ratio of VD to ID, which is equal to VT over capital ID. We call it the small signal resistance of the diode in the forward mode. Because if we look at this circuit, then diode is excited with a small signal and the DC source. So at AC, when we analyze the circuit at AC, when we perform the AC analysis, we kill this source and we are left with only VD across the diode. So diode is excited with this small VD as an AC source, which in response generates small ID current through the diode. So the AC voltage across the diode is small VD, the current entering the positive terminal of the diode is small ID. The ratio of this voltage to that current, if we replace this diode with a black box, then the ratio of the AC voltage across this black box to the current entering the positive terminal of the black box actually gives you the resistance of the black box. So that is why this ratio of VD to small ID is called the resistance of the diode. It is not the actual resistance, it is the small signal AC resistance of the diode in the forward mode. So this because it depends upon the AC quantity. So RD is actually the ratio of the small signal AC voltage across the diode to the small signal AC current through the diode, and hence it's called small signal AC resistance of the diode, or just small signal resistance of the diode in the forward mode. So in the forward mode, in response to VD, the diode acts as a resistance only because VD is given by ID RD. So when diode is excited with an AC source, it behaves like a resistance because its forward bias current is related to the forward bias voltage through RD. So the small signal model of the diode is nothing but a small signal AC resistance, RD. Please note that in this model, I have ignored the effects of the internal capacitances. So this is a simplified small signal model of the diode without such such effects of parasitic capacitances. So here I give a graphical interpretation of what is going on actually, what happens when we impose the small signal approximation. So here I've plotted the ID VD characteristics of the diode, which is just a plot of this equation, and hence is exponential. So Q here denotes the Q point or the bias point. So this vertical line represents the DC biasing voltage of the diode, and this horizontal line represents the corresponding DC current through the diode. So this point marks the DC point on the curve, the bias point on the curve. So if we compute the slope of this exponential curve at Q, at the bias point, then we just differentiate the expression of ID, which is this, with respect to VD, and replace VD with capital VD, because we need to compute it at the bias point Q, at which the voltage VD is equal to capital VD. So when we do that, we get this ratio, where the numerator is the diode DC current ID, and the denominator is VT. So we have already defined ID over VT to be, we've already defined VT over ID to be RD. So ID over VT becomes 1 over RD. So from this expression, we see that RD, which is the small signal model of the diode, is actually the inverse of the slope of the ID VD characteristics of the diode at the Q point. So it is actually the inverse of the slope of the characteristics when where the slope is computed at the Q point or the bias point. So graphically, what happens is that when we apply on top of VD, so let me go back to the circuit. When on top of this biasing voltage VD, which properly biases the diode, when we apply this small VD, so assuming that small VD is sinusoidal, then the input voltage is actually a sine wave riding over this black line, meaning that the input voltage is a sine wave having VD, this capital VD, as the DC offset, which generates an output current, which will be a sine wave riding over ID. So the output DC offset of the total current will be ID. So we'll have a corresponding sine wave riding over ID. So all this small signal approximation does is that it ensures that this perturbation in the form of the small signal, small VD, this perturbation is so small that the corresponding perturbation in the output is so small that the instantaneous points on the curve, they are limited to the region of the curve which can be very well approximated by a straight line. So here I show this black line, which is actually a straight line tangent to the point Q. So the slope of the curve at point Q is actually given by the slope of this tangent at point Q. And you can see that for a region of the curve around Q, the black line very well approximates the blue line. So graphically, what this means, this approximation means, is that we apply such a small signal VD that the instantaneous points on the curve, they are limited to the region of the curve which is approximated by a straight line. This is what it means graphically, to go from here to here. So from this non-linearity, we get an approximate linear expression by restricting the operation of the diode to the portion of the characteristics which can be very well approximated by the straight line. So the small signal approximation ensures that the diode current and voltage are limited to the portion of the ID-VD curve which is very well approximated by the straight line tangent to the bias point Q. So for large input signals, we'll get large output signals, and the instantaneous points on the curve will have large deviations away from Q point, which will break the approximation down. Because if the diode is operating from here to here, let's say, then you can clearly see that this portion of the curve and this portion of the curve, they cannot be approximated with a straight line. So the small signal approximation will break down. So the small signal approximation ensures that the operation of the diode is limited to that portion of the line about Q, which can be approximated by the straight line tangent to Q. This is what it means graphically. That's how we get a linear ADE-VD relation from a non-linear ADE-VD relation. So now that we have linearized or found a small signal linear model for the diode, we can use these mathematical expressions to model the forward biased emitter-based junction of the transistor, BJT. So here I show an amplifier made out of BJT, in which I've excited the transistor or the amplifier with the small AC signal source. So this is the analog of small VD, the small AC source, and then this VBE ensures that the transistor is in active mode. So this VBE biases the transistor in the forward active mode. The overall voltage at the base with respect to the emitter is given by the sum of these two voltages. So this is the DC biasing voltage, this is the small AC signal assumed to be sinusoidal. And the total collector current in the output branch is given by, again, the exponential dependence on VBE. So again, expanding this, so writing this VBE as the sum of these two voltages and separating the exponential term corresponding to capital VBE as IC, capital IC, which is the DC current in the output collector branch, and expanding whatever is left through Taylor series and applying this small signal approximation, we can, on exactly the same lines, again, find an approximate linear relation between IC and VBE, in which the first term is the DC collector current. It is the response of the transistor to the DC voltage VBE, and the second term, which depends on the response, which depends on the small VBE, is actually the response of the transistor to the small VBE, and we call it, we denote it by small I subscript small c. So, like I said, this capital IC is the contribution is the response of the transistor due to the DC bias, and this small IC is the response of the transistor due to the small signal. So again, this is the small signal approximation, and under this approximation, the AC signal at the input VBE is called a small signal. So this is the small signal voltage, and IC small I subscript small c is the small signal current flowing through the collector in response to the small signal voltage. So again, from this relation, if I can find the ratio of IC to VBE. That ratio is IC over VT, and this is called the small signal transconductance of BJT. It is called small signal because both these signals are small, or at least VBE is small, and this is the response to the small VBE. And it is called transconductance because it is the ratio of the output current to the input voltage. So this is the output collector current, AC current, and this is the input base emitter AC voltage. So this ratio of the output small signal output current to the small signal input voltage is called the transconductance by definition. So this is called the small signal transconductance of BJT, which can also be seen to be given by the slope of IC VBE curve at the Q point. So if I differentiate IC with respect to VBE at the Q point, which is set by capital VBE. So after differentiating, I replace small VBE with capital VBE. Then the numerator is again capital IC, which is the DC collector current, and the denominator is VT. So as you can see, it is equal to GM. So GM is also given by the slope of IC VBE characteristics of the transistor at the Q point. So we can shuffle this relation to write the small signal collector current in terms of GM and the small signal base emitter voltage. So IC is GM VBE. Here again, I show graphically what is actually going on here. So these are the IC VBE characteristics shown in blue line, and the vertical dotted line represents the DC input voltage capital VBE, and this horizontal dotted line represents the corresponding DC collector current capital IC. So this blue curve here is the perturbation on top of capital VBE. So this blue sinusoidal signal is actually small VBE. So this is small VBE. So this overall signal is the this blue curve with DC offset given by this black dotted line is the overall base emitter voltage, which generates this overall base emitter voltage, which is riding over the black dotted line, which is the DC collector current in the output. So as you can see that corresponding to this small signal, we have an amplified but still small signal output current. Small because it is linear in nature, because this signal is just a scaled version of this signal. So if we trace the peak of this signal, then the instantaneous Q point. So when there is no signal, then we are at this Q point Q, the bias point Q. When we apply this signal, we get a current at the output. So the instantaneous point on the curve moves up the curve up to this point, which is marked by the dotted pink line. And then when the output collector current swings in the negative direction, corresponding to the swing in the negative direction of the input voltage, then the instantaneous point moves down the curve up to this point, which is again marked by the dotted pink line. So the two signals are still small because they restrict the operation of the transistor to within this region of the curve, which again can be very well approximated by the straight line tangent to the bias point. So again, same graphical interpretation, that the small signal ensures that the transistor operates within the portion of the nonlinear curve, which can be approximated with a straight line. With such a straight line, which is tangent to the curve at the bias point. So this is what makes the output a linear function of approximately a linear function of the input. Now the total base current can be found by dividing the total collector current with beta. So the DC component divided by beta gives us the DC component of the base current, and the small signal component of the collector current divided by beta gives us the small signal component of the base current. So DC component is given by this expression. Small signal AC component is given by this expression, in which again IC over VT is GM. So we get GM over beta times VBE. Now we can invert this expression to compute the ratio between VBE and IB. So VBE, look at this circuit here. So VBE is so if we kill the DC sources to perform just the AC analysis, then the base emitter voltage or the base emitter port is excited by this AC signal VBE, and it due to this excitation, the transistor draws a current IB into the base. So this ratio of VBE to IB, so you can think of the base emitter terminals as constituting a port, which is excited by the small signal VBE, and the current entering the port through the positive terminal of the port. So VBE is the voltage of this base terminal with respect to the emitter terminal. When we are looking at this circuit only, when we are looking at the circuit with no DC voltages, so we are only performing the AC analysis of the circuit. So between the base and emitter, we have this voltage source VBE, which is forcing or inserting a current IB into the positive terminal of this port, uh, made up of base and emitter terminals. So this, by definition, gives us the resistance looking into the port. So specifically, this ratio here, VBE over IB, which is the ratio of the small signal input voltage, small signal voltage between base and emitter, to the current IB, which is the small signal current entering the base. This ratio is called the small signal base emitter resistance looking into the base. Base emitter resistance because we are dividing the voltage across base emitter, looking into the base because we are dividing this voltage by the current which is entering the base. So conventionally it is denoted by R pi and is a resistance, it's a small signal parameter. It's a small signal AC parameter, small signal base emitter resistance looking into the base. So from this relation, we see that the ratio of VBE over IB is actually beta over GM. So R pi is given by beta over GM, and then GM is IC over VT. If we take beta into the denominator, then IC over beta will become IB. So R pi is eventually given by either beta over GM or the equivalent expression or this equivalent expression. Similarly, we can find the total emitter current by dividing the total collector current with alpha, in which IE is the DC component corresponding to capital IC, and small IE is the small signal current component corresponding to small signal collector current. The small IE is the small signal emitter current, which is again because IC is given by small IC is given by capital IC over VT into VBE, and capital IC over VT is GM, so it is given by GM over alpha times VBE. So small IE is the small signal current in response to the small signal base emitter voltage. And again, if we take now this time, if we take the ratio of VEB to minus IE, so we know that IE leaves the emitter terminal. So if we again imagine the emitter-based terminals to be constituting a port, an input port, and if we divide the voltage of the emitter with respect to base, so if we divide the voltage VEB with the current entering the emitter, so the current leaving the emitter is IE, so that which means that the current entering the emitter will be minus IE. So if we divide the voltage of the emitter with respect to base with the current entering the emitter, then this by definition gives us the resistance looking into the emitter. So this resistance is denoted by small RE. So this is again a small signal AC parameter of the device and is called small signal base emitter resistance looking into the emitter now. So VEB over minus IE is actually mathematically equal to VBE over IE because VEB is minus VBE. And VBE over IE can be found from this expression here to be equal to alpha over GM. So small RE is given by alpha over GM. Sometimes you will notice in your textbook as well and in some of the examples that I may solve for you, that sometimes we will take small RE to be equal to 1 over GM. This is because alpha is very, very close to 1. For large beta, alpha is almost 1. Beta is of the order of 100. So even if beta is 100, then alpha is 100 over 101. So that is pretty close to 1. So alpha sometimes can be taken directly to be equal to 1. But nevertheless, here I do not make this assumption. So small RE is alpha over GM, which is given by this expression, equivalent expression, because GM is IC over VT. And IC over alpha is IE. So small RE can also be represented by this equivalent expression. So comparing R pi with RE, because we can write from this relation, we can write VBE as IB R pi, and from this relation, we can write VBE as IE RE. So equating these two expressions, we can write R pi as the ratio of IE to IB times RE. So IE over IB times RE. IE is IC over alpha, IB is IC over beta, so we get beta over alpha RE. And writing alpha in terms of beta, we get R pi as beta plus 1 RE. So this is a very important rule in analog electronics. It's called the resistance reflection rule. So all it says is that since Re is the resistance in the emitter branch, R pi is the resistance in the base branch. So it says that the emitter, the resistance in the base branch, it says that the resistance in the emitter branch is reflected into the base after multiplication with this factor beta plus 1. Or it says that the resistance in the base branch R pi is reflected into the emitter branch Re after multiplication with the factor 1 over beta plus 1, because Re is R pi over beta plus 1. So if you have a resistance on the base side, you can reflect it onto the emitter side by dividing it with beta plus 1. And if you have resistance on the emitter branch, in the emitter branch, then that resistance is seen in the base branch as amplified by beta plus 1. Hence the name resistance reflection rule. This will pop up a lot in our calculation. So collecting these three small signal currents, small signal collector current, base current, and emitter current together. So small signal collector current is GM VBE. VBE is IB R pi. So we get GM R pi VB, GM R pi IB. And we know that R pi is beta over GM. So GM R pi is beta. And then IB is VBE over R pi, and IE is VBE over RE. Re again through resistance reflection rule is given by R pi over beta plus 1. And beta is, like I said, GM R pi. So we get VBE over R pi and GM VBE. So VBE over R pi is IB, GM VBE is IC. So we get small signal emitter current as the sum of small signal base current and the small signal collector current. So using these three small signal currents, we can construct a linear model out of the large signal pi model like this. So this is called the small signal hybrid pi model for the BJT, in which the diode has been replaced with a small signal linear model with the resistance. The difference is that in this case, the resistance is given by VBE, the voltage across the forward bias junction, divided by IB. And that ratio, instead of RD, is now R pi. So the diode is replaced with a small signal resistance R pi. And the source, the collector current is again given by a voltage controlled current source as before. Or it can also be given by a current controlled current source as before. So this small signal hybrid pi model represents BJT as a voltage controlled current source, and this small signal hybrid pi model represents BJT as a current controlled current source. So the two currents, they sum up to give you IE. Similarly, by simple manipulations of these three equations, in which the collector current is given again by GM VBE, but this time VBE, we choose to write it in terms of RE. So VBE is IE RE, and since RE is alpha over GM, so GM RE is alpha IE. So IC can be written as GM VBE or alpha IE. Similarly, base current is given by VBE over R pi. So using resistance reflection rule, R pi is beta plus 1 RE and beta plus 1. So writing beta in terms of alpha, we get 1 over beta plus 1 to be equal to 1 minus alpha. Alpha is GM RE. So we get IE minus GM IE RE. So GM IE RE is GM VBE, which is IC. So we get IB as the small signal emitter current minus the small signal collector current. And small signal collector current, the small signal emitter current is given by VBE over small RE. So again, using these equations, we can modify the T model, in which the diode has been replaced with small signal resistance, but in this case, the resistance is put in the emitter branch. So the forward bias diode has forward bias VBE voltage, and the current through the diode is small IE. So VBE over IE is RE. So in this model, instead of R pi, we have small RE. So whenever you have a resistance in the emitter branch, it will be RE, and resistance in the base branch, it will be R pi. And from this equation, you can see that IB is equal to IE minus IC. So IB plus IC is IE. So IB is IE minus IC. And in this model, I have chosen to represent IC as the voltage controlled current source. So this is the T model, small signal T model representing transistor as a voltage controlled current source. And this is the equivalent small signal T model, which represents the transistor as a current controlled current source, because GMVB is alpha IE. So these two models are equivalent. So far, we have neglected the dependence of IC over VCE. So IC has been given by, let me go back. So IC here has been given by exponential dependence on VBE. So we assume that there is no dependence of IC on VCE. But that is actually not true, because looking at this circuit, if you fix VBE and vary VCE, then base voltage is fixed with respect to emitter and collector voltage is increasing with respect to emitter. This will increase VCB, which is the reverse bias voltage across the collector base junction. So as VCE increases, VCB increases, which increases the reverse bias of the collector base junction. Increasing the reverse bias of the collector base junction increases the width of the depletion region at the collector base junction, which pushes the depletion region farther into the base towards emitter. Hence, increasing the increase in width of the depletion region reduces the effective width of the base, which we denoted with W in lecture 3, I guess. And we saw that the saturation current is inversely proportional to the effective width of the base W. So as W decreases, IS will increase. And since IC is directly proportional to IS, so IC will increase. So increasing VCE will increase IC. This phenomena is called Early effect because it was first studied by James Early, or it is also called base width modulation effect because the width of the base is being modulated. Increasing VCE decreases the base width, decreasing VCE increases the base width. So that is why it is also called base width modulation effect. So this effect actually makes IC dependent on VCE. So as IC, so unlike before, in one of the lectures, I think in lecture 3, we saw the IC VCE characteristics of the transistor, in which in the forward active mode of operation, the curves at different VBE, they were horizontal. There was no dependence assumed taken of IC over VCE. But now we know that IC does actually increase with increase in VCE. So IC VCE characteristics are modified like this. So at a given fixed VBE, in the forward active mode, IC has a correlation with VCE. Increasing VCE increases IC. But when all of these different curves at different VBE values, when all of these curves are extrapolated backwards, they all meet at the same point on the voltage axis. This point is denoted by, because it is a negative point, it is denoted by minus VA. This point is called the early voltage. So the magnitude of this point is called the early voltage, and it is denoted by VA, and it is an important parameter of BJT. It gives the dependence of, it quantifies the dependence of IC over VCE, and has a typical range of 10 volts to 100 volts. So in order to find a relation between IC and VCE, all we need to do is find the equation of this straight line for one of the VBE values. For example, let's say fixing VBE to VBE3, we need to find the equation of this line, green line. That will give us the dependence of IC over VCE for this value of VBE. So we use the 2-point formula for straight line to characterize this straight line, in which one of the points is taken to be this and the other point is taken as the y-intercept of this line. So this 2-point formula gives us this expression of IC versus VCE, in which IC1 represents the y-intercept of the straight line. So what is this IC1? This IC1 can be found by observing the dependence of the slope on VA. So as VA is made large, this point minus VA moves towards the left, and these curves, their slope decreases. So these lines will move in this direction. Their slope will decrease. So when VA is made infinity, then these straight lines, they will become horizontal, and hence will have zero slope. So when they become horizontal, IC in the forward active mode becomes independent of VCE. So it must be given by the usual expression that we have been using so far. So in this expression, if we put VA equal to infinity, then we should get the usual expression that we have been using, independent of VCE. So equating these two, we get IC1 to be equal to this this expression, which in turn gives the total collector current given by this expression. So this expression shows the dependence of the collector current on the base emitter voltage, which is an exponential nonlinear dependence, and on the collector emitter voltage. So again, using the small signal approximation, we can approximate this term with this linear relation, in which VBE over VT has been, this small VBE over VT has been assumed to be much smaller than 1. And then multiplying these two, we get this expression, in which this last term, which is the product of two terms, makes this overall expression nonlinear. But we can neglect this term, because VBE, small VBE or VT is already much smaller than 1. And then this VCE over VA term is also typically smaller than 1. Except for the case when VA is small. So if VA is of the order of 10 volts or so, and we know that the overall voltage can, which is small signal plus the DC, can rise to about VCC of the amplifier, because I'm sorry, half of the VCC of the amplifier, because a good biasing design constraint is that the output DC VCE be biased at 50% of VCC, as we saw in the last lecture. So on top of that, the small signal will vary VCE in the positive direction. So eventually the numerator will be of the order of tens of units, and the denominator is also of the order of, the minimum value is of the order of tens of units. So this ratio is of the order of 1. So which, when multiplied by this ratio, which is much smaller than 1, yields a ratio which is still much smaller than 1. So we can neglect this product. So this is another, on top of this approximation, this is another approximation. This approximation gives us a linear result, in which the first term is the DC collector current, the second term is the increase in DC collector current because of the DC collector emitter voltage. This term is the small signal collector current, and this term is the response of the transistor to the small signal collector emitter voltage. So we write it as, we denote it by I small c comma CE to emphasize that this is the small signal collector current component corresponding to the small signal VCE, small signal voltage component of the small signal component of the collector emitter voltage. So we can again invert this relation and find this ratio VCE over IC. So VCE is the small signal voltage across collector emitter. This IC comma CE is the small signal current due to this VCE entering the collector terminal. So this by definition gives us again a small signal AC resistance, which is a small signal parameter of the transistor. But this time it is the resistance between collector and emitter terminals looking into the collector, because the current moves into the collector. So we denote it by R naught, and from this expression we find it to be equal to VA over IC. This resistance can also be seen to be given by the inverse of the slope of the IC VCE characteristics for a given fixed base emitter voltage. So the slope can be found by differentiating IC with respect to VCE and then replacing VBE with the constant VBE. So this is again the old DC collector current. By old I mean this DC collector current does not show any dependence on VCE. So this is the old DC collector current divided by VA, which is inverse of this. So this slope of the IC VCE characteristics at fixed VBE is actually equal to the inverse of this resistance. So the small signal AC resistance between collector emitter terminals looking into the collector is also given by the inverse of the slope of the IC VCE curve at a fixed VBE. So writing this expression in terms of R naught now, because R naught is VA over IC, and IC over VA is 1 over R naught. So we can replace IC over VA as 1 over R naught. We get the total collector current equal to this expression, in which this term is the new DC collector current, new DC component of the collector current, and this is the new small signal component of the collector current, in which this is the old component, which does not show any dependence on VCE, and this is the new component, which shows dependence on the small signal VCE. So using this information, using this new component of the small signal collector current, we can augment the hybrid pi model and the T model, the small signal pi model and the small signal T model of the bipolar junction transistor with this resistor R naught, small R naught, connected between collector and emitter. Because previously the small signal collector current was equal to GM VBE. For the hybrid pi model, I have chosen to represent VBE, or I have chosen to denote VBE with V pi. Conventionally, it is denoted with V pi, which is consistent with the notation of R pi. So previously, the small signal collector current IC was equal to GM VBE or GM V pi, but now it has this additional component. So there is an additional current which is given by VCE over R naught. So this looks like a term which is given by the Ohm's law. So VCE over R naught is the current flowing through R naught if there is voltage VCE across R naught. So we connect R naught between collector and emitter so that it has voltage VCE across itself, and then the current flowing through R naught, which is given by VCE over R naught, is just this current. So IC is the sum of GM VBE plus the current flowing through R naught, which is because it has been connected between collector and emitter, the current through R naught is given by VCE over R naught, which is this term. So this model takes into account the addition of this term due to the early effect. Similarly, we augment the T model by connecting resistance R naught between collector and emitter. So again, previously the collector current was GMVBE. Now it is GMVBE plus the current through this resistor R naught, which is given by VCE because it is connected between collector and emitter. So the voltage across R naught is VCE. So the current through R naught is VCE over R naught, which is this term. So this augmented T model takes into account the early effect, which introduces this term in the collector current. So please note that I have chosen to not include or show the junction capacitances in this model. So this is a rather simplified model which does not contain any internal junction capacitances. Furthermore, please see that this GM V pi. So V pi is equal to IB times R pi. So GM V pi becomes GM R pi IB, and GM R pi is beta. So it can also be written as beta IB. However, in this case, so previously when there was no R naught, then the current flowing through small RE was equal to the emitter current. So VBE was equal to IE times small RE, and GM times VBE was GM IE small RE. GM small RE was alpha, so GM VBE was alpha IE. But now in this case, emitter current is not the current flowing through small RE because of the inclusion of R naught, small R naught. So emitter current IE is now the sum of the current flowing through small RE and the current flowing through R naught. So emitter current is different from the current flowing through small RE, which is why I denote the current flowing through small RE as IE prime. So IE prime plus the current through R naught is equal to IE, meaning that IE is not equal to IE prime. So now VBE is equal to IE prime times small RE, and GM VBE equals GM small RE times IE prime. So GM small RE is again alpha. So GM VBE becomes alpha IE prime. So it is not alpha IE anymore because of the inclusion of R naught. We have to find a label for the current through RE, and then GM VBE is alpha times that current. So with this, we reach the end of this lecture. Thank you very much for your time, and I will see you in the next class. Take care.